All right, we're back. So I think we ought to be able to finalize our discourse on inverse functions with this final video presentation. Okay, I raised a question: does every function have an inverse? Okay, and so with that in mind, we're going to consider the function y equals x cubed minus 4x. Now, you shouldn't have any trouble trying to graph this because clearly you could factor this and find the x-intercepts and then throw the graph through. So there is the graph of that function. Now, why am I showing the graph of that if I'm asking for uh, its inverse? Well, because the inverse is simply the reflection across the line y equals x. So, here's my line y equals x. Now, clearly, we should be able to reflect that across, okay? We kind of find a couple points and, flip-flop them, okay? Obviously, the point here is a intercept, an x-intercept, so that's negative 2, 0. So its flip-flop would be 0, negative 2. Here is a point 2, 0. Its flip-flop would be 0 would be 0, 2, okay? If we knew what this point was, looks like, let's just estimate it at 1, 4, then its flip-flop would be 4, 1, and this point, which looks like about, negative 1, 3 or 4 would be, okay, 3, negative 1. So that's what you would end up with as an inverse, okay? So say, well, wait a minute. That does not appear to be a function. Okay. Well, you're absolutely right. It's not a function. Okay. But it is the inverse of what we had because it is the reflection of our original function across the line y equals x. Um, so does every function have an inverse? Yes. Is the inverse of every function a function? No. Okay? This is the inverse of our y equals x cubed minus 4x. It is an inverse. It is a reflection across y equals x. Is it a function? No. Okay? Every function has an inverse. The inverse of every function is not a function in this case because it fails the vertical line test. So, obviously. Okay? Um, The inverse fails the vertical line test because now how might we know that ahead of time? Well, take a look at it, okay? Our original function here would fail a horizontal line test, okay? The original function would fail the horizontal line test. Now, remembering when something is reflected across the line y equals x, okay? And when it's reflected across the line y equals x, x equals y, and y equals x. Well, when you reflect a horizontal line across the line y equals x, it becomes a vertical line, okay? A horizontal line reflected across the line, the y equals x line will become a vertical line. And if a function initially fails a horizontal line test, then its inverse will fail the vertical line test. If a function passes the horizontal line test, then its inverse will be a function. If a function passes the horizontal line test, it is tagged as being a one-to-one function. Okay? A one-to-one function is a function that passes the horizontal line test, which is to imply that its inverse will be a function. Okay? Every function has an inverse. However, the inverse of a function is not necessarily a function. We will know if the inverse of a function is a function if we take our original function and ask, is it one-to-one? Does it pass the horizontal line test? For if it passes the horizontal line test, then its inverse will pass the vertical line test and therefore be a function. If a function fails the horizontal line test, it is not one-to-one, which is to presume, okay, its inverse will fail the vertical line test and not be a function. One last concept to talk about. Let's go back to a line, in this case y equals negative x plus 5, and let's find its inverse. Okay? Again, that's what this notation is implying. Find the inverse of the function f. Okay? In order to do that, the function notation f of x is replaced with y. Remembering now what we can simply do is exchange x and y. So that's done right here. Now we want to be able to rewrite this in a function notation, so we want to get y by itself. So I'm just going to just bring the negative y over here is positive, and the x over to the right side is negative. And well, look what we got. We're back to where we started from. And again, since this is a function and it's the inverse of the function, we're going to tag it as such. But look at this. The function and its inverse are one and the same. The function is its own inverse. The function is its own inverse. And how could we verify this? By applying this. F of f inverse is x. Okay? All right? So, and if you were to examine this from a graphical standpoint, it might explain itself. So if we graph this line, okay, if this line f of x equals negative x plus 5 is graphed, you say, what is its relationship to the line y equals x? Well, it is perpendicular to the line y equals x. The slopes are negative reciprocals of each other. And therefore, no surprise, when you reflect this line across the line y equals x, it comes right back on itself. Okay? So you might say, is there a generalization that can be made regarding linear functions which are their own inverses? Yeah. Any linear function which is perpendicular to the line y equals x will be its own inverse. Any linear function which is perpendicular to the line y equals x will be its own inverse. Can you think of any other functions which are their own inverses? Well, f of x equaling 1 over x is its own inverse. You could demonstrate this by composing the first iterate of f of x. The iterate of f of x is, of course, f of x, and you should be able to do that composition and show that it yields x. And in that being the case, you have demonstrated that this function is its own inverse, okay? Because it is a reflection of itself across the line y equals x. And if you take a couple points, that'll illustrate it too. Because if you put in 2, you get out a half. If you put in a half, you get out 2. So all points A, B are also points B, A on that function. And therefore, that function is its own inverse. Okay, so that should do it for our discourse on inverse functions.